Hello and welcome to a small video on the ins and outs of naming covalent compounds. My name is Andy Schweitzer, and a couple of little things here I want to mention to you. Well, first of all, we're dealing with covalent compounds, so you should be aware that covalent compounds form molecules, and because it's a molecule, it's going to form a very discrete package of atoms. For example, we have water, which would be H2O. And in this sense, because a molecule has such a discrete amount of atoms, specific amount of atoms, our formula, our name, is going to also tell us that level of descriptiveness. The formula here is just going to be H2O. This is called a molecular formula. It's giving the exact number of atoms in that molecule. This is a whole item that is self-sufficient, so this is a molecular formula. A molecular formula would, in contrast to what, like an ionic compound, which is just empirical, which would be inherently different in the sense that it would be the simplest ratio of atoms. Now, this is the simplest ratio of atoms by chance. You can't reduce down this number at all, but another example might be, let's say, C6H12O6. This is the compound commonly known as glucose. Now, this is a molecule. It just forms all of these compounds individually, but if you were to analyze glucose, you would see one carbon for every two hydrogens for every one oxygen. This would be its empirical formula, not representing very well the fact that, that this is a bigger molecule and contains many more atoms. But this is the simplest ratio of atoms. All right, so name-wise, how do we give these things names? We'll flip to the next slide, and this is the standard template that we use. Our inorganic covalent compounds we'll be naming will be quite simple. Essentially, they're going to be made of two pieces. The first part here will describe the very first atom, and the second part here will describe the second atom, and that's really all it is. A very common example I like to use would be CO2. Now, the prefixes will give us quantities, the exact quantities listed. So unlike ionic compounds, which never give quantities, these guys always quantities. All right. Now, the prefixes. They are, and I'm just going to type them out because it's a little easier. We'll put it right here. We have mono. We have di. We have tri. We have tetra. We have penta. We have okay, fit all those on there. They are simply 1 through 10. The only difference we'll see between these and the inorganics, or I should say the organic, is the fact that the organic have a slightly different option for the first four. This would be methyl. This would be ethyl, propyl, and the last one is butyl. Organic chemistry has been a little more entrenched, and they have derived these names over historical time periods, so they kept these four. But after that, they all go to, again, the standard prefixes. But for inorganic chemistry, we will not use these. We will simply use the straight prefixes. Okay? The name of this compound, obviously, is carbon dioxide. Very simple procedure. Name of prefix would be one carbon, two oxygens. Now, this prefix, again, says one carbon, but there's no mono here. For whatever reason, simplicity probably, they decided that On the first atom, if it's 1, we're going to drop the mono and just call it carbon dioxide. 1 carbon, 2 oxygens. That little shortcut is only used on the first atom. CO is a chemical that is produced in incomplete combustion. Many of you may have carbon monoxide testers in your house. It's commonly referred to as a silent killer. It's colorless, odorless, causes flu-like symptoms, so can be deadly. But its name is carbon monoxide. Carbon monoxide. So this prefix mono is only dropped on the second one. Also keep in mind, we don't call it monooxide. The O is dropped when you got the multiple O lined up. And that's pretty much it. As we move, we could do a few examples, I guess. Let's say, for example, N2O5. This could be called dinitrogen pentaoxide. Very simple, okay? And of course, if you're going backwards, we could call it carbon tetrachloride. This would be simply 1 carbon and 4 chlorines. This being very straightforward, the biggest issue I find at this point, we have already covered ionic compounds in the previous video. We got this one right here is covalent, is to separate the two as far as ionic and covalent. Okay? A few things, it's utterly critical to be able to separate these two and know which one is which. An ionic compound, for example, is of a cation and an anion. We have a metal and a non-metal. You have to know that all of the metals are located right here. These small section is the non-metals. So a covalent compound is usually a non-metal bound to another non-metal. So they're all from this little section here. As opposed to here, we have a cation anion, which is going to be usually, lots of times, a metal. Grab a metal, grab a non-metal, and you have yourself an ionic compound. A few other things I might note is that the ionic compounds are electrically neutral. Because they have the charges, they are always electrically neutral. So this 3 is coming here, neutralizing the cations and anions down to electrically 0. We don't have this here. CO2 doesn't have any charges. There's no charges to speak of on top of these things, so they don't have any balancing or crisscrossing of charges. You also would note that during ionic compounds, look for some of our polyatomic ions. NH4Cl, ammonium chloride. Ammonium is one of our polyatomic ions, and you should be aware that this is therefore a polyatomic cation, and this is anion, therefore this is ionic, ammonium chloride. This one only gives names. This guy only gives well, it gives both names and quantities, but this is the descriptor between the two. This one gives quantities, this one just does not give quantities. Other than that, this video should encompass a bunch of practice questions to get yourself absolutely proficient at not only naming the two, writing formulas of each, but discriminating between the two. Thank you very much.